Now we're going to talk about systems of first order differential equations. And we're talking about ordinary differential equations. The question is, when would you get a system of first order ODEs? Well, let me give you an example. We've done tank problems before, but what if we had two tanks? We had tank 1 and tank 2. And let's say each of those had a certain amount of salt in them. So we would need two different variables to describe how much salt is in each tank. Let's call this x of t for tank 1 and y of t for tank 2. Let's say there's one pipe going from tank 1 to tank 2 and one pipe going from tank 2 to tank 1. Both of those are going at 8 liters per minute. Let's also come up with an initial amount of liquid in each of these tanks. Let's say one holds 100 liters and the other 200. And finally, let's talk about the initial conditions. Let's say there's no salt in tank 1 at the time 0 and there's 100 milliliters in tank 2 at time 0. And the question is, how would we solve this? Let's first look at tank 1. Tank 1, the rate of change of the amount of salt with respect to time is simply, as before, the rate in minus the rate out. The rate in, well, that's simply 8 liters per minute times the concentration of salt in tank 2. That's going to depend on the variable y, as well as the amount of fluid in that tank. You notice that the rate in and the rate out are the same. The left-hand tank will always have 100 liters and the right-hand tank will always have 200. So that's my rate in. Now let's look at my rate out. What's leaving the tank is still 8 liters per minute, but now it's the concentration of what's in tank 1, and that's x over 100 liters. And we would get that x prime is equal to 8 over 200y minus 8 over 100x. Now I'm going to rearrange that. I'm going to put the x first and then the y. The reason why I do this is it's easier to set things up in terms of matrices if I have my x and y's in order. Now let's do the exact same thing for the second tank. In this case, we're looking at dy dt. And in a similar fashion, I would get this for my y prime. So now I have two differential equations, and I need to solve them both simultaneously. So this is just like in algebra when we had a linear equation and then a second linear equation. We had a system of linear equations, and there were different ways of solving that. We would do graphical methods or elimination or substitution. We're not going to be doing any of that in this class, but what we are going to do is start getting used to putting these in matrix form. So let's go ahead and do that. We usually refer to our vector x as capital X, and it's going to be my two variables x and y. So if I go ahead and think about the derivative of x, then that's equal to x prime y prime. So let's take these two equations and rewrite them in matrix form. Here are my two equations again, and if I write it in matrix form, it'll look like this. And this is what it would look like. Remember, this x prime is simply equal to, in fact, let me replace x prime y prime. And if you remember about multiplication of matrices, we would multiply together this row times that column, and then this row times that column. Let's do one more example. Here's a system of linear equations, and if I wanted to write it in matrix form, it would look like this. Or I could write it more generally as x prime, and this time I'm going to actually explicitly write the vector sign over the x because it's a vector, equals some matrix A times that same x vector, but this time it's just the x vector, not the derivative. And we're going to focus a lot on this form, this x prime equals ax. We're going to say that this matrix A is filled with real numbers and that they're all constants. And we're going to do the same thing that we've done in the past. We're going to guess a general solution. And the solution I'm going to guess is, well, you guessed it, e to the rt. I can't just have a vector be equal to a constant or a number. E to the rt is just a number, so I'm going to multiply it by this other vector, and I'm going to call it u. U will also only have constants, although I'm not going to guarantee that they're going to be real. So just like we did many times, in order to solve this, we're going to now find x prime of our solution, and that's simply going to be r e to the rt and this u vector. So I'm going to go ahead and substitute that into my original differential equation. When I do this, I can see that I can divide both sides by e to the rt. I know I can do that division because e to the something is never going to be equal to 0. And now I'm going to get everything on one side of the equal sign. And that means all of that equals 0. Actually a 0 vector, because remember these are actually vectors. Now I'm going to factor out the u prime, remembering that in matrix multiplication, multiplication is not commutative, so I'm going to be careful to pull that out on the right hand side. This is my initial guess, but this isn't quite right. This A is a matrix, and R is simply a number. So what I need to do is multiply R times the identity matrix. Again, the identity matrix is simply all zeros except for ones along the main diagonal. So if I have this equation, and this equals 0. Well, I don't want u to be equal to 0 because that would be pretty boring. So that means the a minus ri, that is what has to equal 0. Without getting into too much linear algebra, since that is not a prerequisite for this class, I'm going to tell you in order for this equation to be true, all we have to do is take the determinant of that a minus ri and set it equal to 0. That's going to give us a non-trivial solution. So let's go ahead and look at the example that we started with. So right here, this is our A, and what we're trying to do is find R. So this is what I'm trying to solve for 0. So I'm going to replace A with my matrix, and R times the identity matrix simply is R along the diagonal. So that means my matrix is going to look like this. And when we solve this, we will then find our values for R. Remember, when you take the determinant, you multiply this diagonal minus that diagonal. Let's go ahead and do that. That gives us this equation, and when we multiply this out, I get this, and then combining like terms. And I'm not going to go through the quadratic formula because I'm pretty confident you guys can do that. But if I did the quadratic formula, this is what I would get as my two solutions for R. Again, it makes sense that we have two solutions given the fact we have two equations. The whole reason why we were trying to come up with R is we were assuming solutions were in the form e to the rt times u. This vector u we still need to find. So it turns out each of my r's will lead to a different u. Let me show you. This is my first r. We'll call it r1. I'm going to scroll back for a moment. And what we're trying to do is solve this. So let's go ahead and rewrite that. Realize that I forgot my negative sign there. So let's go ahead and put this together. This a minus ri, what it's always going to be is my original values of a, in which case I had -4, 4, 2, and -4. And I'm subtracting from that main diagonal my r. And in this case, it's -4 plus 2 square root of 2, and it'll end up looking like this. So let's go ahead and clean this up a little bit, and this is what I get. This time I'm writing out my vector u as u1, u2, and my 0, and I should have always been having a little vector symbol above that, as 0, 0. So now what I'm going to do is multiply this out to solve for u1 and u2. It's not obvious, but row 1 and row 2 are actually linearly dependent. If I went ahead and multiplied my first row by negative square root of 2, you'd be able to see that the two rows are in fact linearly dependent. So if they're linearly dependent, it means they're basically the same equation, which means I have one equation and two unknowns. That means I'm never going to be able to get a single answer. All I'm going to be able to do is get a certain relationship between u1 and u2. And it turns out there's actually an infinite number of u1 and u2s that go with a particular rate that I've chosen. And let's go ahead and see what I mean by that. If I multiply that row times that column, I will get -2 square root of 2 u1 plus 2u2 equals 0. I'm going to go ahead and rearrange things, do some simplifications, and I finally get it down to this form. So what I'm going to do is come up with a vector that represents the relationship between u1 and u2. This is something that I always trip up on if I'm not careful. Whatever's multiplying the u1 is what you want to be put in the u2. And whatever coefficient is multiplying the u2 is what goes in the u1 position. Because think of it this way. If I let u1 equal 1, this 1 I'm going to plug in for u1. 1 times square root of 2 is square root of 2, and that gives me what should go in u2. So you're always just switching the numerical coefficients. So if I put my r and my u together, this is what I get for one of my solutions. Now notice, I said there was an infinite number of u's that would go with this r1. I could have left this unsimplified. This u vector is also the correct solution. There's an infinite number of u vectors that correspond to a particular r1. And let's demonstrate this by dealing with our second r value. And now I'm going to stop calling them r1 and the u vector and use the real terminology. The r's are called eigenvalues and the u's are called eigenvectors. Let's find the second eigenvalue. That is my r2, which I said was -4 minus 2 square root of 2. And I want to find an eigenvector associated with that. So I'll do the same thing I did before. I'll have my a minus ri times u equals 0. This is what I get when I set things up with my second eigenvalue. And now I'm going to go ahead and solve for an eigenvector. That's my first step. And then I'll take, again, just one of the rows because these are actually dependent rows, and I come up with the following. Here are my u1 and u2s, and that gives me the following. Again, you use the opposite numerical coefficients. So where does that lead us? That leads us to our final solution. And that's my final answer. You might wonder what happens if we could have a possible infinite number of eigenvectors. Well, once you have a specific initial condition, that C1 and C2 are going to depend on the initial condition, and that will be different depending on what eigenvector you chose. So if I give you an initial condition problem, we'll all have the exact same answer. If I wanted to rewrite this in terms of two separate equations like before, all I would do is split up my matrix like this. So let's review the steps we're going to use to solve this type of differential equation. First, we find our eigenvalues. In order to do that, we take the determinant of a minus r times I and set it equal to 0, and we solve for r. Our next step is then to find the associated eigenvectors with each eigenvalue. In order to do that, we use the following equation. And finally, we build our solution given those two separate values, like so. Now, of course, we could have 3 equations or 4 equations, but then we're going to have 3 by 3 or 4 by 4 matrices. And on exams and even on homework, we're not going to be doing too much of that. We're going to mainly be sticking with two-dimensional systems, that is, an x and a y.